Is my screen visible to everyone? Okay. So first of all, we will discussing question number 8. It's a really simple problem. It just gives you a value n, and each you can do operations like you can select that n and divide that by 4. Basically, the 4 floor value. For example, let's say there's 7. You will divide it by 4, and you will end up with 1 instead of being 1.75. It will be 1. So floor division. So you will be doing this up until and unless the x reduces from 3 or it gets equal to 3. So you have and each time you do the operation, the x keeps on multiplying by 2, basically the number of coins. For example, if I show you here, for example 16. So the value of the coin is 16. So at first the value of the coin is 16 and there are 1 coin. Then it will get converted to value 4 with 2 coins, and then value 1 with 4 coins. You cannot do it any further because it is lesser than 4. So you cannot do this any further. Now you are asked to find the maximum possible value for the given n. So you can see here examples, other examples as well. For 1, it will be 1 only because you cannot divide it any further. For 5, you will do the floor division, so it will become 1, and the 1 coin will become 2 coin. For 16, I just showed you, it will be 4. And for this large number, it will be something like this. So how do you do that? You can just run a while loop until unless x reaches a value below 3. You will keep on dividing it by 4. Given it will give you a time complexity of log base 4 n, which is acceptable here, I guess. 10 to the power 18 log base 4 is a very small value. So let me just show you the implementation. So you can see here, first of all, we'll be taking the input. Then I'll be marking the first coin being 1. Of course, we will give him 1 coin, so 1. And until unless n reaches the value of 3 or lesser than that, we'll keep on dividing it by 4 and multiplying the answer by 2, and we'll just output the answer. Is the logic and the implementation clear to everyone? Okay, the question was very simple. So I'll be moving to question number B. Now this here is kind of an interesting question, I'd say. More of an intuition based, I'd say. Atram wrote digit D. Basically, you will be given a number, and for n factorial times, you have to write D, 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 and continuously like that. So, and then you have to output how many digits from 1 to 9 are from 1 to 9, all the odd digits. How many odd digits will be able to divide this enormously large number? At first, it might seem like a bit of difficult to solve, but you can solve it using the divisibility property of each of the numbers. Of course, 1 will divide every number. Then coming to 3, we will just check if the summation of all the numbers is divisible by 3, which of course is not possible here to check because of this large value. We'll be taking n factorial of this, so it will be really, really large value. We'll be checking this also. And for 5, we will be just seeing if the last digit is 5 or not. Basically, D value must be 5. I'll come to each one of them individually in more detail. And for 7 also, we will just look at a pattern. And for 9, we'll again be using a divisibility rule. So um, let me just So let's say a number, let's say d, and it continues like this, and there is d and d. So what will it take for it to be divisible by 3? It will always be divisible by 1, right? Because d, every number is divisible by 1, right? We will always be printing out 1. Now let's look at 3. So the summation of all the d's, basically d into n factorial, should be divisible by 3, right? It should be divisible by 3. If this is satisfied, then yes, we can say the entire number will be divisible by 3, because this is the divisibility property of 3. But the issue here is that we cannot just calculate n factor, because the value will be up to 10 to the power 9, and 10 to the power 9 factorial will be an enormously large value which we cannot compute. So what can we do here? We can see one pattern. First of all, if d value is um 3, 6, or 9, then obviously the entire number will be divisible by 3, because d itself is divisible by 3, so the entire number must be divisible by 3. But if say d value is not equal to these numbers, instead let's say, for example, let's say 2. So how can we find a number at which n? Because see, d will never be divisible by 3 in this case. So we'll have to find n value for which will be divisible by 3. So if we look at it, what is 1 factorial 1, 2 factorial 2, 3 factorial 6? So in case of 6, if you look closely, what will be happening here is that there will be a d multiplied by 6 into n minus 3 factorial. I can write this, right? And this number will always be divisible by 3. So we will be just seeing if n is greater than or equal to 3. In that case, if d is not this, it must at least be, the n should always be greater than or equal to 3, provided the d is not equal to 3, 6, or 9. If this is satisfied, then yes. So I guess the divisibility test for 3 is clear to everyone. Now let's look for number 5. So for 5, the last digit should be 5. What is the divisibility test for 5? The last digit should be 0, or it should be 5. So it's pretty simple. If d is equal to 5, then only it will be divisible by 5. Otherwise, not, right? If it is true, then yes. Otherwise, no, it won't be divisible. So 5 1 is really simple. Now here comes 7. If you look closely at 7, any number, it may be 1, 1. It was a bit of more observation based, I'd say. 1, 1. Up to 5 digits, no number which has all the digits same is divisible by 7. So if you can check it on the calculator or something. So the first digit that is divisible by 7 and it has all digits same, it is 6 times 1. Basically 6 lakhs 11 1 lakh 11,111. So this is the first number which has all the digits same. I'm assuming d is not equal to 7. Sorry, I'm assuming d is not equal to 7. In that case, the all the numbers should be equal to, the digit must at least be 6 if all the digits are same. So the first numbers of such type is 1 1 1 1. Of course, if d is equal to 7, then all the numbers having d equal to 7 will be divisible by 7, because you can just write it as 7 times 10 plus 7, or maybe 7 times 100 plus 7 plus 10 times 10 plus 7, like this. So it must be always be divisible by 7. Whereas in case of other numbers, when d is not equal to 7, it must at least be 6 digits. Of course, now if 1 is divisible, the 1 is divisible by 7, in that case 2 will also be divisible. 3 will also be divisible, because you can just write it as this times 2 or this times 3, like this. So it will always be divisible if the digits are 6. Is up to here clear to everyone? Okay. So it must always be a multiple. It will be a multiple of 3, 2, 5, 6, 7, or whatever the value may be. So here, by this we can check for 7 divisibility for 6 digits. Now what about digits greater than that? Of course, like we can write this as, you can just multiply it by 10. Now if we look closely, since this number here is divisible by 7, of course, since it was divisible by 7, so its multiple of 10 should also be divisible by 7. But we have added a number here which is not divisible by 7. So the number 1, 1, 1, basically 7 times 1, will obviously not be divisible by 7, right? Because we have added a number to a number which was divisible by 7 and added a number which is not divisible by 7. So obviously the entire number won't be divisible by 7. So by this logic, you can see if you multiply it by 100, the same case will still apply. So up to, until unless this value reaches 10 to the power 6, and making this number also the same number as like this only, it will always be divisible by not divisible by 7. So by this logic, the d should either be equal to 7, or n should be greater than or equal to 3. Why I'm saying 3? Because remember that we are calculating here a factorial. So there will be n factorial times d. So n factorial d. So 3 factorial is basically 6. So there will always be 6. So, so there will be d n factorial times. And since it will always be divisible by 6 if n is greater than or equal to 3. So the entire number will always be divisible by 7. Up to this is clear to everyone? Okay. So now I'll be moving on to divisible test for 9. Now see, for 9 it will be a bit more case-wise. There won't be a single case which will just solve the entire thing, just like we saw in previous cases. We will be checking, see, if d is equal to 9, then obviously it will be divisible by 9, because the entire number will be d 9, 9, 9, 9, 9, 9, 9, and obviously d times n factorial is divisible by 9, because d is equal to 9. 9 times n factorial is obviously divisible by 9. So for a d equal to 9, the entire number will be divisible by 9, because the divisibility test for 9 is the addition of all the digits should be divisible by 9. Now, if we come to other numbers, Let's say D is not equal to 9. It is not equal to 9. So obviously we will need a number such that the entire summation should be divisible by 9. That means we will be relying on this n factorial. There will be special cases, but let me look at the general case. For example, D is 7. For 6 and 3, there will be a special case. But for, let's say for 7, the case for 7 will be same, for 2 also, for 1 also. So there should be a factor of 9 here. So which is the first number which has this? It is 6. 6 is the first factorial which is divisible by 9, and its value is 720 if I'm not wrong. It is 720. So it will be divisible by 9 if and only if n is greater than equal to uh, 6. So this is one condition. But if we look closely, we can also have a 3 factor in D as well. We can have a 3 factor in D as well if D is either, let me just erase. We can also have a 3 factor if the D is divisible by 3. For example, let's say D is 3. So we have already a 3 factor. So in order to make it divisible by 3, we only need one 3 in n factorial, right? Of course, if the number is greater, then it will be more beneficial. But even if we are able to access one 3 from here, it will be divisible by 9, right? So if so, the condition changes to for D equal to 3 and 6, because 6 also has a 3 inside it. It is a factor of 3. So for 3 and 6, if n is greater than or equal to 3, then also this is valid for 9. So this is the condition for 9. I hope it is clear to everyone. Okay, so I'll be moving down to the implementation part. See, as I told you, every number will be divisible by 1. So I'm just printing out 1. For D equal to 9, 6, 3, or for other numbers, but n is greater than 2, because n greater than 2 basically implies that the n will be 3 or greater. It will always be divisible by 3. I just showed you that. For 5, the only and only condition that is applicable is D must be equal to 5. Otherwise, it is not divisible. And if it is equal to, then it is always divisible. For 7, I just showed you that also. It must always be equal, either D should be equal to 7 or it should be greater than equal to 3. And for 9, either D should be equal to 9 or n should be greater than equal to 6, or n should be greater than equal to 3, but only for D should be equal to 3 or 6. So this is the implementation. It's a very simple implementation base. Just you need to observe how division is taking place, especially for 7. The solution that I wrote for 7, I cannot prove it mathematically, but it's something that I observed myself. So I hope the implementation is also clear to everyone. Okay. So from here, Pranava will explain question number C and D. Thank you.
Am I audible? Okay, let's get into the problem C. So in this problem, we are given an array which has 1 and minus 1, and only all the elements are either 1 or minus 1, and only one of the element is different. Okay, let's understand how to solve this problem by an example. So let's take the first example test case. We are given an array.
Radhav, your screen sharing is not working.
Oh, yeah. Yes. Yes. Okay. Is my screen visible? Yeah. So in this problem, we are given an array. It has all the elements equals to -1 or 1, and only one of the element is different. And let's understand how to solve it. Let's take an example. So let's take the first example test case. So in the first example test case, we have the elements 1, -1, and then a couple of ones. So this is the example test case. And now, first of all, this is the different element, right? So we can simply split the array into two parts. So let's just split it. This is the first part, and this is the second part. And let's forget about the different element. We'll deal about it later. So basically, now we'll first find the different subarray sums we can produce in these two different arrays, which have only one and -1. After that, we'll think how can we calculate the other subarrays which include the element 10 or the different element. So here we have 1 and -1, right? So I just have a point here. So we have an array just like ones, it has ones and -1s, so whatever it may be. So what is the minimum sum we can produce? It is nothing just but the maximum number of consecutive negative ones we can get. Is my point clear? Maximum number of consecutive negative ones we can get. That is the minimum sum we can get. And similarly, the maximum sum we can get is like maximum number of consecutive ones we can get. That is the maximum sum. Like here in this sub array, we can get sums range from range like the maximum sum we can here positive sum we can here get is like 6, which is this subarray 6, and the sum we can get is from -2 to 6. This is the range you can get any sum. Like it's greedy algorithm. Like we'll just basically find the subarray with the maximum positive sum as well as the negative positive sum, maximum negative positive sum, and then we can produce any sum in that range. Is my point clear? Like it's a standard greedy algorithm. Yeah. So if this is clear, then the problem is just really simple. Like we simply reduce the problem into two. We have two subarrays, right? Okay, so we have two subarrays. Suppose here we have a -1 and a 1, and here we have 1 and 1. And now in this subarray, we can produce all the sums from -1 to and 1. It's clear, right? We can produce every sum. 0 is obviously present because it's an empty subarray. We don't need to think about 0. So we can produce every sum from -1 to 1 in the subarray. Is this clear, right? Any confusion? And similarly, in the second subarray, I can produce the sums from range 0 to 2. Like it's just about the greedy algorithm here. Like we need to take the maximum sum we can produce and minimum sum we can produce, and the rest of the things we can adjust. And now these are the sums we can produce in both the arrays. We'll just push all the sums we can produce into the set. Like that's what I have done. And now we have to deal with those subarrays which contain 10, and we get some different sum, right? So in order to take 10, like we have this, so we can either take a subarray like this, somewhat like this, whatever it may be, and this and this. Three kinds of subarrays we can pick, including the left one and including the right one and including the both. Is this clear, right? We can take three types. Either we can take the subarray with having x and then the rest of the elements in the left and right parts. So if this is clear, then we'll move on. Am I audible? Yeah, we have three cases, just that's it. we're gonna pick the element in this range, or we can pick it from the left subarray, left part, and right part also including, and both. Just we need to deal all the three cases. Just a minute. Yeah. So now we have minus 1 1 and 10 1 1, right? So suppose now we need to calculate what are the sums we can get including this element in the left part. So we can get sums like from ranging from 0 to 1, right? It's a greedy algorithm. You can easily calculate what are the sums you can get. Suppose we can get the sum from L1 to LR1 in this subarray, including this element. This is important. And we are able to, in this subarray, we are able to get, including this element, we are able to get L2 to somewhat like R2. Then my point here is, when we combine both of them, we can get somewhat a range that is L1 plus R1 plus X to L2 plus R2, L1 plus L2 plus X plus R2 plus R1 plus X. Is this clear? Like we just sum the both the ranges. Is this clear? And if this part is clear, then problem is simply reduced, right? We find the ranges we can produce in this subarray, and then in this subarray, including this element. This is important. And then we'll just simply add it the middle element, which is simple. Is this clear, right? Or any confusion? We just add the both the inequalities to get that equation. Is this clear, or any doubt, whatever? Okay, if this part is clear, then it's simple, right? We just find the ranges in this, including this element. This is important. So we need to include that element. That is important. Whatever it may be, you need to include this element and take a subarray like this. Whatever, you need to include this. And you need to just find the range, what you can get. Like I've already explained it. So let's get into the code then if it's clear. Okay, so let's get into the implementation. Yeah. So basically I've taken the input here, whatever the array it is, and I've initialized the whatever the, I mean, a different odd element as different element as it is in the 0th position. You can take it anything, it does not really matter. And now after I got it, I just break down the loop and I just made the x equals to that index. And initially that's what I've done. I've used the greedy algorithm here to find the range of the sum that I can produce in the left subarray, which we split it into three parts, right? The middle element is different, left part and right part. This is for finding the ranges in the left subarray. What are the sums we can get? And after that, I pushed all of them into the set. And then similarly, I've done for the right subarray. This is a standard greedy algorithm. Like I'm not getting the name, whatever it is. So we just find the right subarray sum which we can produce using this greedy algorithm. I mean, like, do I have to explain the algorithm, or you guys can look it up? Like this is a standard greedy algorithm. Yeah, it's fine then. Yeah, I've just simply inserted them, all of them, into the set. I'm here using the set because it just gets rid of the extra elements, whatever unique elements will be present. And similarly, now I have, this is important here, like I've talked about it, like this, including this element, right? You need to take the subarrays including this element. So in order to include this element, I have done that. I've started from x minus 1 and went to this, and similarly found the range, whatever it is. And similarly, I have inserted this, that element, and we can also include ax, right? The center element can also be included. So I've just inserted both of them into the set. And then similarly, I found that I've started from x plus 1, like I've started from this region here, and I found out the range, whatever I can get. Like it must be like contiguous here, like it must be continuous because you need to take a subarray, right? So here that's it. Like I found out the minimum sum and the maximum sum and we got the range. And similarly I have inserted that also, like somewhat like this segment sums, this segment what are the ranges we can produce, like, and I've inserted them. And then finally whatever I've talked about the summation, right? This summation, we should also insert this summation because we are including the center element and the left parts as well as right parts and whatever the sums we can get. So I've just started from first L1 plus R1. This is minimum 1 plus minimum 2 and maximum 1 plus maximum 2. And I've just inserted them into the set and then finally printed the answer. Like any confusion, whatever it is at any part. Any confusion or is it clear? Like, okay, if it's clear, then I will stop. Or I have to go problem 4. Let's move problem 4. Four. Yeah. So in the problem 4, we have given 3 integers L, R, and G. And we have to find 2 integers which are in the range L to R. And their GCD must be equal to G and the distance should be maximized and A should be minimized if there are multiple answers. So here we are given 2 integers, like here we are given an L and an R and a G. So obviously if the elements A and B have a GCD of G, they both must be divisible by G. Like is this point clear? Like both must be divisible by G. Yeah, both the numbers must be divisible by G. So somewhat like it will be having A element will be having A1 into G and B element will be somewhat like B1 into G. Somewhat some coefficient is there. But here my point here is like where the GC must be equals to G. It cannot exceed G, right? So here these numbers A1 and B1, whatever they are there, their GCD must be equals to 1. Otherwise, our condition will be violated here. Is this point clear? That A1 and B1 must have a GCD of 1 because or else the GCD will not never be, it will exceed G, right? Because somewhat extra prime factor will be there which will cause lead to the exceeding of the GCD. So similarly, let's try to find the minimum and maximum possible values of A and B here. Minimum and maximum possible value. Like we know that minimum possible value can be the seal of L by G for A1. Minimum possible value of A1. Like is this clear? Seal of L by G because that is what we have to make it right. Seal of L by G. So if the seal of L by G is part is clear, right, then the B1, this coefficient, other coefficient B1, it can be right. It can be the like here you should take the this one like greatest integer of R by G. Is this part clear? Is this clear, right? You have to take the box greatest integer because or else it will exceed R. So now you've got both points, right? So now let's understand this thing. We have to make GCD of A1 and B1 must be always equals to 0, right? Equals to 1, right? Or else our GCD will exceed G. So we have two numbers, right? Now the problem reduces into two numbers. Suppose let's take some examples, right? Suppose we have a number like 1 and a 9 and we have to let's take some somewhat different numbers like 5 and possibly you can take a 12. These are like let's assume that these are A1 and B1. Like we have to make the GCD as 1. Here is GCD already 1, right? Let's take 15. Yeah, here GCD is 5, but we need GCD of 1. Like it's quite evident that we can increase the numbers. Like we have to just make slight changes in them. Like we can increase A1 like up to 1 point. Let's increase A1. Like we made it 6 and we maintain 15. Here now GCD is still not equals to 1 because there is a GCD of 3. So suppose let's increase it again by 1, like 7 and 15. We are increasing a1, like we have to adjust, right? So here now the GCD has become 1. Now my point is we can make the GCD 1 really quickly, like in no time, like just by adjusting somewhat. Like any confusion here, it's just intuitive here. Like my point here is like we can make the GCD 1 just by making slight changes in the both the numbers. It's difficult to prove this, but it's quite intuitive here. You can get it. Or anyone has any doubt here, like we can make the GCD 1 really quickly. Like we have to increase A1 by some X units and decrease B1 by some Y units such that their GCD becomes 1. Is this clear? Like their X and Y are really small. Like they cannot exceed 100 because we need the maximum range, right? Maximum range we need means we don't need to go really big. Then the range will reduce. So we simply try to brute force here. First of all, we'll find the A1 and max A1 and B1, and we'll simply brute force for the X and Y by running a 2 for loops and simply find the maximum range. Is this clear? Or any confusion, any doubt, whatever? Yeah. So we'll just simply brute force for X and Y. I have just took 20 here. Like you can take 100, but it may lead to TLE. That's why you have to kind of take it wisely. Yeah. So if this part is clear, then it's simple, like brute forcing, just that's it. So first let's get into code where it's, yeah, here it's, yeah, let's get into. So I've taken the input L, R, and G, and I found here this is A1, nothing but A1. Like this is the seal value L by G upon plus L percentage G not equals. This is just the seal value, and this is the floor value, whatever floor value, like maximum value and minimum value. Like this is A1 and B1, whatever I've talked. And similarly, we can now, yeah, where is that? Yeah, here now I've just run a 2 for loops, just brute forcing for the values of X and Y. Brute forcing for the values of X and Y. Is this clear? Uh, am I audible? Yeah, brute forcing for the values of X and Y. I've just took 20 here because I mean, like the calculate, we have to verify the GCD also, right? The GCD parts takes log n time. So we cannot go further long because log n is huge here. Like it's gonna take 64 iterations. So closely, like that's it. So I've just brute forced for X. This is the X. This I is nothing but the X which we have talked, and the Y. So we are increasing the minimum value L1 by X, and we are decreasing that maximum value by J. And what we have to ensure here is that maximum value must be always greater than the minimum value, right? Or else it doesn't make any sense to take the range. And the what I've talked about is the GCD must be 1, or else the GCD will exceed G. It's not going to be G. And whatever we have the range, I've taken -1 initially because to check that the answer is valid or not valid. And then I just calculated the distance, whatever distance. If it's greater than the reference, I've just modified the difference. And the only thing matters is the first element because we can similarly calculate the other difference as we have the difference. So if the difference is -1, there is no answer, obviously. We cannot find any pair. And if the difference is not there, means it's going to be G times C because this is, we were just talking about the coefficients, right? This is the A1 and this is the B1, whatever. And we simply print the answer now. It's simple. Does anyone have doubt or, yeah, then I just.
Okay, Pranava, the entire explanation is done, right?
Yeah, it's done. Yeah.
Okay, so we conclude here. Thank you.